As we have progressed through this chapter, the thought may have crossed your mind, how in the world is this mathematics? There's no numbers, there's no equations to solve, and there's no graphs. Well, the logic that we're exploring underlies all of the theorems, all of the logic that governs the things that we do in math. It can feel a little bit abstract, so the point of this section is to help you to understand these basic truth tables with a concept that is familiar to you. In section 3.3.2, we will examine truth tables and their connection to electric circuits. Now, you don't have to be an electrician to understand this. If you have a light switch in your home, this will be a familiar concept. Did you know that logic can be applied to electric circuits? Consider the light bulb that is turned on or off by one switch. So here's my light bulb and here's my switch. In the diagram below, the light will be on if the switch is in the up position. So if I take this switch and I turn it or put it in the up position, then the electric current is going to be able to reach the light and light it up and get back to a closed loop. Anytime there's a closed loop, electricity can complete the path. The light will be off if the switch is in the down position because the loop is broken and the current cannot reach the light. So there's no way for it to complete a closed loop. So when the switch is in the down position, the light is off. So essentially, we could say the switch negates the light. If the light is off, then the switch in the up position would negate it and turn it on so that it's shining. Or if the light is on, we can negate that by putting the switch into the down position and turning the light off. So if you have a basic light switch in your house, think of it as a negation. The light switch negates the truth value of the light. So what we're doing here is saying that the state of being off and the state of being on is like true or false, and the switch negates those conditions. Got that? Now let's consider a single light controlled by two switches. Do you have a light like this in your house? Maybe you have a light in your dining room or something, and on one side of the room there's an entrance with a light switch that turns that dining room light on or off, and then on the other side of the room at a different entrance there's another light switch that you can also use to turn the light on and off. So if you have a switch like that in your house, think about that as we explore the conjunction and disjunction truth table. In the first circuit below, the light is going to be on if both switches are in the up position. That's because if both switches are in the up position, we have a closed loop for electricity to flow around and continue keeping that light burning. The second switch is a little bit different. In the second circuit, the light is going to be on if at least one switch is in the up position. For example, we can turn this switch into the up position, and then the electricity has a closed loop to flow around and continue lighting that lamp. The other possibility is to have this one in the up position. Well, the electricity still has a closed loop to flow around and to continue lighting that lamp. It's also possible that we have both switches in the up position, and then the electricity can flow around a closed loop through either switch. Now, if we let a 1 represent a switch that is in the up position, and 0 a switch that is in the down position, then the light will be on is 1, off is 0, according to the following tables. So this table on the left corresponds to the circuit on the left. Let's suppose that switch 1 is in the up position and switch 2 is in the up position. Notice that would give me a closed circuit for the electricity to flow around, so the light would be on, and we can code that as a 1. In the second possibility, switch 1 is in the up position and switch 2 is in the down position. So I'm going to call this one switch 1 and this one switch 2. Well, if switch 1 is up and switch 2 is down, then electricity does not have a closed loop to flow around. So the light would be off, and we'll code that as a 0. Next possibility, we're going to say switch 1 is in the down position and switch 2 is in the up position. Well, that's the same problem we had on the previous row. There is not a closed loop for the electricity to flow around, so the light is off, and we'll code that as 0. And finally, let's look at what happens when both switches are in the down position. In this case, again, the electricity does not have a closed loop to flow around, so the light would be in the off position. Now, if this reflects the wiring in your house, it's a little bit inconvenient, and sometimes those things just happen. In order to turn this light on, we would have to turn both switches into the up position on both sides of the room. There is a better option. Our second circuit is going to correspond here to this second truth table. Let's call this one switch 1 and this one switch 2. We'll begin by assuming that switch 1 and switch 2 are both in the up position. This creates a closed loop, even though you've got a couple of options here. There is a closed loop that the electricity can flow around, so the light would be on. Now, the second option will say switch 1 is up and switch 2 is down, as we have right here. We still have a closed loop, so the light would be on, and we will code that as 1. Next possibility, switch 1 is down, switch 2 is up. So we have created a closed loop, therefore the light is on, coded as 1. The final possibility here, both switches are down, and in that case the loop is broken, so the light would be off. Now, if your house is wired that way, that's more convenient, because notice in that case, I could either have both switches on, I could have one in the up position or the other one in the up position in order to turn the light on. That means I don't have to have both switches turned on in order to turn the light on. Now, if this looks familiar, then the fundamental pattern that you're recognizing there is basically the difference between a conjunction and a disjunction. These are the basic truth tables for and or in a slightly different form. Now, we learned how to form the truth table for a conjunction, two simple statements connected by and a disjunction, two simple statements connected by or in the previous video. The only difference here is that we were using ones and zeros applied to the electric circuits instead of T for true and F for false. But let's look at the pattern. Here's our conjunction, P and Q. Recall from the previous video that a conjunction is true only when both components are true. Every other time it is false. Notice this pattern. A 1 with 3 zeros is similar to a T with 3 Fs. The code is simply different. Instead of a T, we have a 1. Instead of an F, we have a 0. The second truth table here corresponds to the second setup for our switch, which remember was more convenient and more flexible. Remember, the rule for the disjunction is it is true if at least one component is true. Or we can remember a disjunction is false only when both components are false. So a disjunction, remember that's P or Q, is true except for that last possible case. Notice the result of light switch setup number 2 is very similar to the disjunction truth table. This one is 3 T's followed by an F. This one is 3 1s followed by a 0. So if you can associate these truth tables with what you know about light switches and buildings, I hope that gives you a deeper understanding of how to judge the truth value of a conjunction and a disjunction. By the way, modern computers that we use every single day perform all of their operations on 6 basic logical connectives: the not, the negation, and or. Those are the 3 connectives that we've studied. Also, there's a couple of more connectives with computer programming: in and in or. Exclusive and or exclusive or. And the last one is called XOR, for exclusive or is what I meant to say. Can you imagine your computer works with zeros and ones to perform its tasks, just like we study truth tables with T's and F's. So binary code, zeros and ones, very similar to what we're calling true and false. So again, I hope this helps to shed a little bit of light on how to judge the truth value for a conjunction, a disjunction, and also the very simple negation.